large part of this work is done in collaboration with a few key collaborators up here, and I would just like to acknowledge them. All right, so I'm a grad student, and okay, so goal over this talk, I would like to just very, very, very briefly summarize where we are at detecting high redshift galaxies. And by high redshift, I mean a redshift 4 and above galaxies forming before and during reionization, those guys who actually reionize the universe, and what JWST I hope they can find. And also illustrate how a number of planned upcoming instruments, not just JWST, but also Euclid and WFIRST can work together, and how the synergy can really boost our understanding of high redshift galaxy population. And of course, all of these are from a galaxy formation graduate student point of view, also theory. Meaning that I'm really looking forward to actually using Origin Space Telescope when I flip through the interim report from last year. Okay, and that's the reason why I still have this old image stick in there, because, I know it's outdated. I learned it last night at dinner, but that's the thing I read. Okay, next time I talk about it, I clean it up. So let me start with what I actually do. So I am a member of a JWST early release science team. I'm with Sears, and I've recently just joined the WFIRST science investigation team. And my job there is to supply mock catalogs. I'm sorry, Kartik, are you? No, okay. I know he just hates mock catalogs. Okay, so I created mock catalogs for these kind of upcoming surveys, very similar to what the Candles team had, and is using the Santa Cruz semi-analytic model. And we hope that this will help optimize observing strategies in the future, and also how to even use this telescope, and what do we expect these future telescopes to see. So this is a mock image that we created in collaboration with Greg Snyder, Harry Ferguson, my boss, Rachel Somerville, and some other colleagues for upcoming JWST survey. I'm not sure if I can show it, but I ask around and no one stops me, so I guess I can. All right, so don't blink and look up. And here we go. It's a fairly large image, and I can zoom in for quite a lot. This is and also pan it across. So we hope to detect these galaxies. So this is not just a mock image, but this is also going into the pipeline where we're developing for the ERS survey. And these galaxies are predicted based, so it's based on dark matter halo simulation called Bouchard-Planck in light cone format produced by Peter Baruzzi using the Santa Cruz semi-analytic model. And then these galaxies, because it's a SAM, I'll explain what a SAM is. I'm obligated to by this point. But this galaxy's image, spatially resolved image with the disk size and height, are from illustrious original galaxy, the original simulation. All right, so why do we care about them? Because these galaxies resembles the progenitor of our Milky Way galaxy, and these might as well be the ones who reionize the universe. We just don't know, and we don't see them just yet. So we want to be able to see them and understand them, at least quantify how many are there out there. All right, so we have heard SAM, or the semi-analytic model, several times today. But let me just quickly explain what it is. So when I say I do simulations, if what pops in your mind is a box of particles evolving, spinning spiral galaxies, galaxy colliding, and then exploding supernovae going off, blowing gas out, or large-scale structure cosmic web like that Millennium simulation, get all of those out of your mind. Okay, it's not that kind of simulation. So SAM, let me just, not criticizing, but with all due respect, conventional numerical simulations are awesome because they allow us to recreate and to witness physical processes that way we may never be able to see with a telescope, and we learn physics. But they're very expensive. Imagine you're giving a fixed amount of computational power, certain amount of CPU and time. Then you inevitably, and a box full of particles. And inevitably, you have to decide on how big of a volume do you simulate and at how high resolution. So either you have a really big box with very low resolution, or a small box with very high resolution and not very many massive objects. So the SAM is trying to simulate a wide mass range of galaxies at a relatively low cost, and I'll get into that in a bit. So we start off with a set of physical parameters. These parameters are, for example, these three listed here related to star formation, how star formations can scale with either cold gas or molecular hydrogen. But with a set of physical parameters that are only calibrated once at redshift 0, and we do not return that at high redshift, otherwise it loses its purpose. We use a list of carefully curated physical recipes to trace how baryonic processes will shape global galaxy properties inside dark matter halo. So that's the SAM. And then we run the SAM down a dark matter halo merger tree, meaning that this is the dark matter halo merger history. We care about the progenitor mass and when a merger happened, the merger history of a dark matter halo. So these can either be extracted from n-body simulation or be constructed using extended press tractor, as Chris mentioned in his talk. So for this project, we use EPS. And we just run down the tree and trace how galaxies inside this halo evolve with the SAM. And we get a list of physical properties out at the end. So this is great. It's efficient. And then we forward model that into observables that all the observers are interested, like what you can actually see with a lens and telescope. All right. So let me get some of the things out of the way. So I already mentioned that the SAM is only calibrated once at redshift 0 with a subset of observations. So this is the calibration plot. Blue line is the SAM. And this is the predicted stellar mass function from redshift 4 to 10. And this is very encouraging because we do not need to include new physical recipes. We do not need to retune any parameters. And we can naturally produce the needed required evolution of stellar mass function that fits the current observations, which is amazing, I think. At least that one thing we can say is that we include to the first order the important processes that needed to shape the stellar mass population. And besides that, we can also fit observations to star formation rate function simultaneously, again, across all available redshift. And the UV luminosity function. So the dashed line there is without dust, and we have to put in some amount of dust and assume some attenuation to get the luminosity function to work. But because it's the same, we get a wide range of physical properties out fairly easily. So we can also cross-correlate all of these properties and get to know what the high redshift galaxy populations are like. All right, so these are the pros and cons. The SAM really operates across a very wide mass range. So we go down to the atomic cooling halo, all the way out to the very massive things that are reasonably rare at at a given redshift. And we're very efficient, as I mentioned several times. We can process millions of halos overnight on the laptop. And we are really, really efficient that I have to say that again because we can easily rerun the SAM and just change the physical parameters and see how modeling uncertainties, there are things that we don't know. How would that change or how would that impact our predictions? And we can also control what physics goes in there. For example, in the past, we had this cold gas-based star formation recipe, and now we have molecular-based star formation recipes. And we really see that it makes a difference. However, there's also, I'm not saying the SAM is great at doing everything. There are things that we cannot do. For example, we do not spatially resolve our objects, because as Rachel would put it, the SAM is modestly a simple bookkeeping scheme. We keep track on how things get change from one thing to the other, how hot gas cooled and cold gas, how cold gas forms stars, how stars turn to supernovae, how they reheat gas and then push out material. But we do not spatially resolve our galaxies, so we cannot tell you, okay, there are a bunch of stars in one side of the galaxy and there's none on the other side. We do not do that. Also, there are several other shortcomings, but you can check it out on your own. All right, so back to the question, what can JWST see? So this is the stellar mass function. Just for this one time, replace them with the assistive axes. So the vertical shows you the count in terms of volume, density, and the x-axis shows you the stellar mass, lower mass to the left, and more massive objects to the right is basically a histogram of stuff. The data points up there are the latest observations from Duncan and Mimi Song. And yeah. So the blue lines are prediction. As I mentioned, we have a really huge dynamic range. So that turnover in the low mass n is not from the resolution, but rather from the atomic cooling limit. So we're just not able to cool those halo at that mass range, and there's nothing forming there. I mean, the number of low mass galaxies start to drop off. So the vertical green dotted line there shows where things become too faint for an hypothetical JWST-wide survey. So things become too faint to be seen, and that vertical line marks where the detection limit dropped to, the completion dropped to about 50%. And the horizontal line marks where one object is expected per survey volume. So this is just a very rough estimate. Of course, you need more than that to do statistics, but I just want to mark that, that horizontal line there to show you that everything that's below that line would be a little too rare to expect it to be found with JWST. Okay, so we can really see that as we go with deeper survey, lens survey, we can probe further down in the low mass end slope of the stellar mass function or the faint end slope of the UV luminosity function. And this is really important because the observations do not tell us anything. There are two sets of them, they don't agree with each other. And we just don't know if there's anything out there. HST don't see it, VISTA don't see it. So maybe there's just nothing out there. I certainly don't hope so. So we need JWST to see it. But the other thing is, oh yeah, and also we can do that for a wide range of redshifts. So we can easily go up to redshift 10. And all of these can also go down to redshift 0. I just didn't show them. Right. But the more important question is, what can we learn from a model of this kind? So I'm just showing you one example here. So this is the equation we use for mass outflow. So mass outflow is scaled by some efficiency, and then is a power law with the circular velocity. So what happened is, this parameter here, alpha reheat, is tuned once at redshift 0 to such that the stellar mass function match observations. But there's no guarantee that this efficiency or coefficient stays the same at high redshift. So and even observations don't give us any clue because there are two sets of them, and see if even I perturb the parameter a little bit, it's still within the current observation limit, the uncertainty. So so this thing, I'm just demonstrating that if we turn feedback stronger, then there are fewer galaxies forming at high redshift. And if we make feedback weaker, then there are more low mass galaxy forming at this redshift. And so we need future telescopes to tell these, to help us constrain our model, perhaps. But as I mentioned earlier, this is, I have to brand this to a year ago when I published the first paper, semi-analytic forecast for JWST, so people actually read it. But these predictions are not actually just for JWST, but they are good for everything that comes after JWST with stronger sensitivity, with wider survey area, anything that is capable of detecting high redshift galaxies. So this is actually for JWST and beyond, and with multi-instrument synergies. All right, so back to the JWST scenario. This is for deep survey. You have seen this from the last slide already. What if we put two more instruments on there? Let's say Euclid and WFIRST, all for some reasonable assumed deep survey. So if we put them all there, you can see that JWST can detect this bunch of galaxies at redshift 4. And hopefully WFIRST will take care of this patch. And then Euclid will take care of some more. No, it doesn't work that way. Anyway, so this is something I'm hoping for that to happen. And we see that as in some part of the patch, there's some great redundancy. So hopefully that will help put a few more data points on the photometric detection, and hope to get the SCT feeding works better that way. Okay, but at redshift 10, the landscape kind of changed because we need the sensitivity of JWST to get something out of there. But these things are really faint. Otherwise, the more massive things are just becoming too rare for the field of view of JWST. And WFIRST hopefully will be able to cover this patch, and Euclid, if it does what it does. Okay, but the point to make here is at redshift 10, we really need all of these instruments to fully sample the full mass range at redshift 10 for the stellar mass function. Again, I did this for a wide range of redshift, and I have to apologize because this plot was made a year ago for another talk in another conference David Spergel organized, but LSST was on there, actually. SST was on there, and the color scheme doesn't match what shows on the left. But so yeah, we need all these telescopes, and they work together. So from a different perspective, this is the UV luminosity rest frame versus stellar mass plane for redshift 4 and 10. So this is what I hope JWST will be able to cover. And then WFIRST, and then Euclid. This is just a fun and quick way to demonstrate how these instruments work together and provide joint constraint to fully constrain the entire galaxy population. and we have one model that can make these predictions for the entire galaxy population. All right, so I've been talking a lot about multi-instrument survey, but all photometric and all surveying starlight, UV emission from res frame redshifted into infrared. But besides that, we can also conduct multi-tracer survey in conjunction with ALMA. So JWST and some other instruments will enable us to survey this, stellar properties from these high redshift galaxies. But with ALMA, we'll hopefully be able to probe some of the gas property as well from molecular emission. So this is some predictions that was done in collaboration with Gergo Popping. So this year he published a paper on the arts of modeling molecular gas emission, and this vertical axis, this emission is from his model. So by putting these two together, we can already make some predictions for how ALMA and JWST can work together and constrain both the gas and stellar properties for high redshift galaxies. So where does Origins fit in the lineup? So I must say the first talk from this morning has really beautiful slides, and one day if I talk for Origins, I will steal some of those for my own talk. But this is what I have for now. Also from these figures are from the interim report from last year. So Origins is a powerhouse for spectroscopic survey. Just imagine for the next 10 years when we have first JWST and then Euclid and NW first. The amount of photometric detection will build up in our bank, in our database. We'll have a lot of them. And I think Origins will be the telescope that I'm hoping at least, I envision Origins to do a spectroscopic follow-up for all of these galaxies. I'm saying all. I'm really hoping that happens. And on the other hand, the SAM itself can also make prediction for future Origins spectroscopic follow-ups. So instead of besides just the standard, synthetic SED based on SPS model that's based on the metallicity and age of the stellar population, we're also adding in molecular gas emission in collaboration with Gergo Popping's model. And besides that, we're also collaborating with Michaela Hirschman, that she models the nebula emission. So that will put a few more emission lines on our spectra, and we can also make predictions for OST. All right, so I do have plenty of time. So besides of just testing them against galaxy detections, we're also working on multiple fronts. I myself coupled the SAM for galaxy formation with a reionization model. So now we can also test the galaxy population, but with IgM and CMB constraints. So it might be a little out of interest of the audience here, but just advertisement. Paper 3, 4, and 5 might be out soon. So JWST will be able to detect, the most exciting part is, maybe for galaxies at redshift 6, they're responsible for about 80% of the ionizing photons. So yes, we're not seeing the entire UV luminosity function, but maybe we can see enough galaxies to confirm that galaxies did reionize the universe. Yes. All right, and just another quick plug. So I'm wrapping up my PhD in a year, and I've been making predictions for this telescope a lot. But besides that, we also need to upgrade the model itself to make it more robust at high redshift, to make more robust predictions for these future telescopes. So I've been trying to launch this project. The acronym has been approved, and there's a logo, but no paper written yet. It's called the Semi-Analytic Model with Ultra High Redshift Astrophysical Interplay, or SAMURAI. So, right, I love this name, and I really hope to just bring this project to life. So the idea is that we have a well-established Santa Cruz SAM that makes predictions that work for now. But in the future, we need to, if we try to go up to redshift 15, we need to implement physical processes that we know in matters at high redshift, but we still don't have. For example, self-consistent stuff for population 3 stars, and maybe the creation or destruction of dust, along with a few others. So just a quick plug, and if you have an idea, have a strong preference of physical processes I definitely should include in my model, please tell me. And as an observer, in the next decades or two, if there's anything that you really want me to make predictions for very quickly, please also let me know. I will try my best to incorporate those. Here's my summary. So we learned that it's an exciting time to study high redshift galaxies, and we have a line of instruments that can do it. And Origins is going to be a great addition to the lineup, and I really sincerely hope that it really comes to life so I can actually use it. And our group will continue to develop many bells and whistles to improve the semi-analytic model to make more catalogs and predictions for these future telescopes. All right, thank you.